Welcome back to our third video discussing different units of concentration. We just came from talking about the mass volume percent, which express the mass of solute per total volume solution, and then made the percentage by multiplying by 100%. And in that conversation, we kind of contrasted mass volume percent to what we've seen as mass percent in Gen Chem 1 when talking about like the composition of a compound. So I want to kind of circle back to that idea of mass percent or weight percent. And I want to give us a definition of weight percent that isn't just, mass of part over mass of whole, but I want us to be specific about what weight percent could look like when expressed for a solution. So weight percent, just like any other percent, a part over a total. Here, if it's by weight, this is going to be the mass of solute expressed per mass of solution and then scaled to make a percentage. So if we are going to be looking at mass percent, then we are looking at mass of solute when talking about solutions over mass in total of the solution times 100%. This is our kind of basic definition of a mass percent, weight percent. And again, specific to solutions. And once again, we have something that we need to be mindful of. It is that same rule of physics that we just cannot ignore nor escape. So we have to remind ourselves that the law of conservation of mass, matter, is a thing we have to obey. So this means that the mass of solution, as we discussed in our density video, has to be equal to the mass of its components. So mass solute plus mass solvent. So if I want to express a mass percent equation for a solution, I could write it as either, it's like kind of short form, mass of solute over mass of solution times 100%. And this is equivalent to mass of solute over the sum of solute mass and solvent mass times 100%. So these are both expressing the exact same thing. It's just sometimes maybe we don't know the exact mass of solution, but we can solve for the mass of its components. So this is why it's a good idea to just remind ourselves of this unbroken rule of the universe, law of conservation of matter. So it's popped up 3 times now when talking about solutions. Now, mass percent, we've seen it before. It's like useful. Let's see here. Yeah, this is useful when like maybe we don't have an idea about what the nature of the solute is, meaning the identity of the solute. So if we don't have a way to get into moles or something like that, then this complete mass ratio expressed as a percentage is a little bit easier to deal with. However, it's not what you're reading when you're reading like, your household items, right? You're very rarely expressing a solution in terms of mass percent. You're doing mass volume percent, but that doesn't mean this is something you won't ever see. So now let's get into these fun ones. And I say fun because these ones, the parts per units, are really interesting because they are units that are exclusively used when we are talking about quantities of solute that are very, very, very small. So to give you an example or an idea, some of you may know this. My spouse works in a lead sampling lab, and so they get people that bring in, leaded paint or soil that they think might be contaminated with lead. Air filters that they think might have aerated particles of, lead oxide in the atmosphere, something like that. And it's their job to use a highly analytical or precise instrument to quantify exactly how much lead is in the sample that the customer is bringing to them. And they are measuring in what's called parts per million. And there's some limitations on how many parts per million total parts of a sample can be lead by nature. Typically, like, hopefully under, I think, like 50, 20. The limitations keep getting more and more stringent, which is good, right? We don't want lead just around everything, right? But I think this idea of maybe like a part per can be a little confusing at first. So part per something, this language of part, right? We've seen it in our discussions of other ways of expressing concentration because concentrations are proportions, aka they're fractions. So part is just like the part in a fraction, right? Part over whole. The question is, depending on which of these three definitions we're looking at, PPT, ppm, and ppb, what is the whole? So what is the denominator in this unit expression? So PPT equals parts per thousand. That's where the T comes from. So T, 1,000. ppm is parts per million. And then ppb, even more dilute, B, that is parts per billion. So depending on what kind of level of like diluteness we are looking at, so how dilute our sample is, the whole could be either out of 1,000, out of 1,000,000, or out of 1,000,000,000, which expressed just kind of using shorthand. So not quite scientific notation, but like exponents. 10 to the 3 is 1,000. So 1,000 parts. 10 to the 6 is million. So per million parts. And then 10 to the 9 is billion. So we're looking at a total billion here in which we can have a certain number of parts. So if you're looking at these parts per thousand, parts per million, parts per billion concentration unit and asking yourself, like, what is a part? Because that's still just like a really abstract idea of like a fraction of something, right? Part over whole. How does this relate to solutions? I think that's a good question that might be coming to your brain at this time because we have a couple of different ways of talking about parts. but I think we should probably stick to the way that is most common to us in terms of how we might see a solution being prepared in the lab. So when we're talking parts per definitions, like parts per million, parts per billion, etc., what does that mean? We often express our part in a mass unit in grams. So for example, a part per 1,000 unit says that if I have 1,000 grams of solution, then one of those grams of solution, like 1 ppt, has to be solute. Same thing with ppm, 1 ppm. If I were to hand you 1 million grams of solution, then one of those grams would be due to the presence of solute. And parts per billion, following this trend, if I were to hand you 1 billion grams of solution, then 1 gram of those billion grams would be the solute. So parts per 1,000, parts per million, parts per billion, talking about grams of the solution. Now, let's think about this a little more practically, right? If I hand you 1,000 grams of solution, I'm handing you, if it's aqueous, more or less a kilogram of solution-ish, right? Like, right, 1,000 kilo, yeah. That's fine. Like I could go grab a kilogram of solution, its volume probably would be around this range, right? Something I can handle. A million grams, that's where things get kind of big, right? Like 1 million grams of solution, that is 1,000 kilograms of solution, so pretty heavy. And then 1 billion grams of solution, that's even more insane, right? That's 100,000 kilograms. So how can we like maybe massage these units so that the part per unit doesn't lock us into these insane masses of solution? And the answer to that is, let's make this, instead of an expression of 1 always in the numerator, let's put the 1 always in denominator. So what might that look like? So if I had 1 gram solution in each of my cases. All right, parts per. This is saying 1/1000th, right? So I need to think about what unit needs to go here such that I have 1/1000th. So what is a number that when I divide by 1 gives me 1/1000th? And the answer to that is the milligram, the 1/1000th of a gram. So 1 milligram of solute per gram solution. So we have now taken that per 1,000 and utilized the milligram-gram relationship to express that per 1,000 in a way that doesn't require us to go actually gather 1,000 grams of solution. What about parts per million? So I need to think about what number gives me a millionth of a gram. Like I could write 10 to the negative 6 grams, but we have a unit for that, right? We have micrograms of solute. So if we're talking about parts per million, we now have that 1 to 1 million relationship here with the microgram. And then looking at parts per billion, right? How do I get 1/billionth? That's 10 to the negative 9. Well, negative 9, that's nano. So we've got nanograms of solute. And that's now where we get our super tiny quantity. So these are our dilute concentrations. So this is what like I would use. Like if I were in the lab, these are the versions that I would use here. I think like these are the ones that are a bit more practical, but kind of depends on what you're doing. Now, I do want to make a quick note about these like incredibly dilute concentrations, right? A part per thousand is dilute compared to like a molarity, right? But a part per billion, that means like we have very, very, very small amounts of solute present in our solution. So if that's true, right, like if we do have a very, very tiny amount of solute present in our solution, then oftentimes what we will do is we will express these in terms of volume. So you might see microgram per liter or nanogram per liter when using these incredibly dilute concentrations. And it's going to be per liter of solution, but that approximates to the liter of solvent when you have such a small presence of solute, right? Like if I literally handed you again, think about a beaker that has a billion a billion solution molecules in it. If that is a 1 ppm solution, then only one out of those billion particles in solution is the solute. So that means that 999, I don't know, a bunch of nines, like we are one away from a billion in the millions, right? That is going to be the amount of solvent. And that's basically the entire solution, right? So sometimes you'll see people make little adjustments where they express this in terms of total amount of solution, either in terms of solvent, which is valid. It's like a valid approximation when, again, you're looking at such dilute concentrations like this. But it's not the strict definition. This is like another approximation of these units. And again, I would really only ever trust this approximation for the ppm or ppb. Okay. So we have gone through all of our new units. And in our next video, we're going to practice this ppm, ppb, ppt idea. We're just going to make sure we're super comfortable with the idea of what it means to be like a part out of a whole and how we can take that ratio of 1 to 1,000, 1 to 1 million, and 1 to 1 billion and make sense of it if we were actually given a concentration unit like we are here. And then once we've practiced our ppm and ppb, that's when we're going to get into the process of converting concentration units. So like, let's say I had the molarity of a solution, but I wanted to know its molality. Or let's say that I had the mole fraction of solution, but I actually really want to know its mass percent or mass per volume percent. How would I make those conversions? So this is where we're headed, concentration conversions. We need this skill because, as mentioned when we discussed molality, our very first new unit, this is incredibly important to us when we talk about colligative properties, which is why we've been talking about solutions so intensively in the first place, right? We're trying to understand what's going on in a solution, what the components are, the interactions are, and how we describe them mathematically. So then we can look at how solutions' physical properties may differ than those of pure solvents, which is a really fascinating idea. So we'll have some practice with ppm, ppb, ppt, and then we will talk about concentration conversions in our next video series. So thanks, guys.